So we're going to talk about gas evolution reactions. As the name suggests, a gas evolves, gas is produced in one of these reactions. So we have two aqueous solutions that mix, and a gas is formed, and the gas bubbles out of solution. Usually we see bubbles or fizzing happening. Some reactions form a gas directly from the ion exchange. So this is an example where potassium sulfide and sulfuric acid, we swap the ions, we get potassium sulfate, which is a soluble ionic compound, and H2S, which happens to be a gas and will bubble out and it smells horrible, by the way. Other reactions, the gas is formed by the decomposition of one of the products. So here we have sodium hydrogen carbonate, also known as baking soda, plus HCl, and we get sodium chloride and H2CO3, which is carbonic acid. But carbonic acid is not stable, and so it decomposes into water and carbon dioxide gas. And so those are the types of reactions that we'll mostly be talking about. Here's an illustration of that happening. A solution of baking soda being poured into an acid solution, and bubbles form. So when the hydrogen ion here attaches to the hydrogen carbonate ion, it forms carbonic acid, but then it doesn't stay together. It comes apart into CO2 and water. Yes?
Isn't it a neutralization reaction is acid and base? So with sodium bicarbonate, wouldn't that be like a base?
The sodium bicarbonate does act like a base here, yeah.
But it's not forming a salt and water only, it's forming a CO2 gas, so that wouldn't be classified as neutralization.
Well, it is technically a neutralization reaction as well, yes. Because it does form, it forms water and a soluble ionic compound. It also forms CO2, but there's no exclusion for that. So these are the types of gas evolution reactions that we should be able to recognize in Chem 1A. The first one is just when you have H2S form. So when does this happen? Well, you just do your ion swapping. You know, we got this pair of ions coming to the party and this pair, and let's swap partners and see how people get along, right? So if H2S is one of the results, it's a really smelly gas, and it bubbles out of solution. Nobody wants it around, I guess, and just goes away. So we just have to remember that. The good thing is, I mean, this is not a huge part of the class, but I have to tell you this. These three groups form intermediate products that are unstable. So we just talked about carbonic acid, H2CO3. Sulfurous acid is another one, and ammonium hydroxide. So if one of these is the product of our ion exchange, then we need to know that this is going to be unstable and decompose and form a gas. Now the good thing is there's a nice pattern here to what gas is formed. So if we look at H2CO3, and we have H2SO3, and we have NH4OH. They are all going to decompose to form water and something else. So they're all going to make water plus a gas. Now, the formula for the gas you can figure out by just removing two hydrogens and an oxygen from this formula. So to remove a water molecule, I have to get rid of both of those hydrogens, and I have to get rid of one oxygen. What's left? CO2. That's the gas. With H2SO3, losing a water molecule, remove 2 hydrogens and an oxygen. There's the 2 hydrogens gone. Remove the oxygen. What's left? SO2. That's the gas. Also stinky. Sulfur things don't generally smell very good. NH4OH. Again, just take 2 hydrogens and an oxygen out. So I'm going to take out that oxygen. There's 1 oxygen. I'm going to take this hydrogen and 1 of those hydrogens, and what do we have left? Ammonia, which is a gas. Also doesn't smell good. So any questions? You just need to recognize these 3 intermediates, that they decompose to form a gas, and that if you get H2S as a product, it's a gas. It's just something you remember. Write a molecular equation for the gas evolution reaction that occurs when you mix aqueous hydrobromic acid and aqueous potassium sulfite. So we start out with writing the formulas for the reactants. Hydrobromic acid, what kind of an acid is that? Binary or oxyacid? Yeah, it's binary because of the hydro prefix. So binary acid, we've just got hydrogen ion and the anion, which here would be bromide. And so because of the charges of those ions, we know to put them together like that. It's aqueous. And potassium sulfite. Well, potassium's K+. What's the formula for sulfite? SO3, 2-. Those things from that memorization quiz are not going to go away, so keep those flashcards. And then predicting products, it's always a good idea to start with just exchanging ions, swapping ions. Say, well, what happens if we put the H+ with the SO3 and the Br- with the K+? Again, we always have to have the positive ion first and the negative ion second. Tradition. Fiddler. KBr, is that soluble or insoluble? Soluble. All potassium compounds are soluble. And then the other one is going to be hydrogen ion with sulfite ion. And based on the charges, we put those together and we get H2SO3. That's sulfurous acid. Are we done? Do we have a gas? We don't have a gas. This is unstable. This is not going to stay that way. So I'm going to erase this bit down here. So this is unstable, and it's going to decompose to form water, H2O, plus what's left when I remove the water molecule from the H2SO3, which would be the SO2, and that's the gas. So I've got HBr aqueous plus K2SO3 aqueous. It's going to form KBr aqueous plus H2O liquid and SO2 gas. Is it balanced? No. What jumps out that's not balanced? The potassium. So there's 2 potassiums over here and there's 1 over there. Well, I could fix that by making this 2 KBr. So potassium's good, potassium, and then, well, let's look at the Br. 2 Brs here and only 1 over there. So I need to put a 2 in front of the hydrobromic acid. And then I need to check out the sulfur and the oxygen. Now this is a situation where that SO3 ion fell apart, right? So we can't balance it as a unit. So here's one sulfur and one sulfur. And over here I have 2 oxygens plus 1. It's a total of 3 oxygens over there and 3 oxygens over there. So it worked out. Any questions?
I don't know, what if on the, you have an extra hydrogen on the left?
Well, we've got 2 hydrogens here and 2 hydrogens there. I forgot to check those, but yeah, they're good too.